Stanford University.
Okay, so this is lecture 7, Parallel Patterns 2. We'll kind of continue in the same vein as the last lecture, I guess last week, on kind of higher level abstractions. I'm first going to talk about segmented scan, which is kind of a more complex scan or structure built on top of the regular scan. Then about sorting, which comes up basically everywhere if you're doing almost any kind of parallel programming, and certainly on CUDA. Then about this kind of now pretty popular pattern called MapReduce, which is a very generic pattern of doing things, but actually is very useful. So if people don't have a real idea of how to write a specialized kernel, how to attack certain irregular problems, they first think of MapReduce. And I'll talk a little bit how you can do that on CUDA. And finally, I'll talk about kernel fusion, which is this pattern of how to combine simple kernels or kernels with certain communication producer-consumer patterns together into a single kernel. And basically what you get out of that is you reduce memory traffic to and from global memory. And that can, especially if you have lots of small simple kernels, that can be a real savings. So with that, let's dive right into a segmented scan. So as the name implies, it is a scan, but it is working on segments. And what that means is that instead of doing an operation which touches all your data, so let's say you do a prefix sum across all of your data, or a minimum or a maximum across all of your data and get one result back, you can indicate lots and lots of regions, very small, very large, determined at runtime, over which you want to do an operation. So again, very similar to scan, and you'll get lots of results out. So if you have something where you don't know until you've actually touched the data how many regions you're going to have, how many blocks you're going to have, and how big and where those are, then segmented scan is kind of the operation for you, because that means that you can operate on all of your data at the same time with one kernel call, instead of basically having to read out all of your little regions and launching a kernel each time and doing a scan or whatever it is you have to do on them. And it works by basically augmenting the normal scan with a secondary array which has flags or barriers in it. So let me just kind of walk you through what you have up top. At the top array I'm showing here is the flag array. And so everywhere you have a 1 indicates a new region, a new segment is starting. And if you have 0, that means I'm just part of the previous segment, whatever segment I'm currently at. And then the second kind of array, the second line, are the actual values. Is that clear so far? So in a segmented scan, what will happen is you will do an operation on the region you're in. So basically, before up to the next one. And so here, if you're doing a max, you can see that. So you have the first region, the first segment is the first 3 values, right? And then if you do a max, well, it's all 0. The values are all 0, so you're going to get 0. And then you have 1, 3 here. So the same as in a scan, you would get, in a global scan, if you had 3 would be your biggest value, then you would have 3 basically in the whole array. But in segmented scan, you'll get 3 just for the segment until you have to hit the next 1 in your flag array, which you do here in the second to last value. And then you get 6, and in this, and then you get the 6 in that particular part of your array. So notice again the difference here is if you had done a global max scan, you would have gotten 6 everywhere, and you wouldn't have gotten individual values. And so if you have if you need this, the max or the sum or min or what have you over lots of little regions or big regions, then this can be very useful again, because you can do you can run it all in parallel and not have to do lots of little calls. And how it actually works, so kind of I showed you the result. Here is kind of how you do this, prefix sum, but now it's segmented prefix sum. So the normal scan operation which I kind of walked you through last time when we had a lecture. And so every time you have a 1, kind of a barrier, so you don't have, there's a barrier, and you don't propagate the value across that barrier. So if you look at the communication patterns here, this is kind of the same communication pattern as you saw in scan, where first you do the sum with your direct neighbor. So 1 plus 4 is 5, and so on and so forth. And then you do the sum, partial sums of the element 2 away from you, and so on and so forth. But where you have a dotted arrow, you don't propagate that value to the next element, but you basically, in this case, propagate 0. So for different types of scans, you'll propagate different kind of null values, right? If it's a max, you'll probably propagate minus infinity. Or if it's a min, you'll propagate plus infinity. And if it's a sum, then it's 0. If it's a product, it's 1, and so on and so forth. So segment scan kind of needs to know that, because every time it encounters one of these barriers, it basically has to propagate this fake null value across, as opposed to the real value which you would get in a regular scan. And so now that I've kind of shown you in graphics form, let me just quickly show you the code, just the one very small piece of it. So as in normal scan, you have a data array in shared memory, and you load that up. But you also have this flag array. So you also have a secondary array in global memory where each element says, I am the start of a new segment or not. And if it is, you set a 1. If not, you set a 0. So once you've copied both of those values into their particular arrays in shared memory, and you've made sure that everybody has written, and then so that's why you call sync threads. I'm kind of showing here just one iteration, the very first iteration. So here this basically says, you'll notice this step here, right? That's the regular scan of the, in the first iteration. You just go to your direct neighbor and you add it up and you store it back. But notice here that the difference here is now that if the flag array was 1 at that particular location, and you just directly propagate, there's no add. And because it's, so this is, S data at IDX plus 0, kind of obviously implied. And if you don't have that barrier, then you just do your normal scan operation. At the same time, you're merging your flags as you go up, and that's basically an OR, a logical OR. So if you don't remember from your class in C programming, this is logical OR. This is basically saying, is either one of these values 1? If either one of them is, you write 1 at that location. And so, here the offset is 1. The same way with scan, you increase your offsets always by a factor of 2, and you do a downsweep and then an upsweep. And what this gives you, I won't show you the whole code because it's, scan was already pretty complex. Segment scan is even more complex. But it's basically the same exact pattern as scan, just that you're operating on the flags array at the same time as you're operating the data array. And on the data array, you're looking at not just the actual data, but also taking into account, what value you have at that location in the flag array. Does that make sense to everybody? Okay, great. So after having kind of shown you, what it can do, so where would you use it? I think I've mentioned most of this, but think of back, if you can, to part 3 in MP1, where you had to do an iterative PageRank calculation. If you remember there, for each element in each iteration, you looked at a variable number of neighbors, took those inputs, and summed them up, if you remember that. So in the actual implementation, what you probably did was you basically did a serial sum for each element in each thread. But think of if you wanted to have that unrolled even more, the full parallelism. Because the number of elements which contribute to each element is variable, and you wouldn't know what to do, you wouldn't know for each one how much there is because the graph could be changing, for example. Segment scan would be exactly what you wanted to use in that case, because doesn't matter if you're adding 2 elements or if you're adding 1,000,000, you always will get the right result. And you would not be forced into basically writing specialized kernels for kind of different graphs. Oh, this graph has a very regular structure that you always have 5 neighbors contributing some value to the next output, and this one has lots of 1s and 2s and one with 1,000,000, right? Segment scan takes care of all of that, and the efficiency basically for all of those different versions is the same. Now, that being said, segment scan is usually less efficient than a specialized kernel if you have very irregular patterns, right? If you have exactly 5 neighbors adding to the final value of any particular element, then you probably want to write a kernel for that, because segment scan, the same way as scan, you have to do at least 3 kernel calls. If you remember, segment scan, calculate the partial sums, calculate the block kind of offset sums, and then you calculate the real values in the end. Same way for segment scan. So if you know exactly how many neighbors you have and you can fit those nicely into kind of per block, then you only need to do 1 kernel call, and it's probably more efficient. But if you have structures where it's very hard to predict, what their structure will be, graphs come to mind, you have irregular sums, stuff like that, then segment scan basically you can use that one generic pattern, and you can use it everywhere. And you don't have to write specialized kernels for different data types and data input patterns. The other one, which kind of is you're generating basically outputs in a new domain. So you're saying, I am going to be, for each element, I am going to be part of some domain X. Think of MP2 when you were binning, right? The first output was, oh, each particle is going to be part of some bin. And then you used atomics to append and put those particles into each bin. What you could have done is just said, oh, I'm just going to give you the ID of my bin, write it straight out, no atomics necessary, and then you can call a sort, and then all the elements in a particular bin would have been contiguous, in a case sorted, and then whatever you wanted to do per bin, if it's a min, if it's a max, or if it's a sum, or if you want to find the 5 minimum closest neighbors, which we did in MP2, you can do that, again, with segmented scan. The pattern holds. Obviously, the operator, what you're going to be doing is changing. It's not going to be a sum. It's going to be more complex. But again, you could have done that no matter that some bins were half empty and some of them are basically full. Or even if some bin was completely empty, it would have been fine. It would have segment scan would have dealt with that and would have just basically skipped it. So this pattern of, determine a new ID for each element, sort based on that ID, and then operate on those regions or whatever you want to call them with segmented scan is actually very common. And I'm going to come back to that in a slightly different context in just a moment. So, and I should also mention that in a similar way, segment scan is very useful if you want to do kind of divide and conquer or recursive type algorithms. So I remember several of you have asked, kind of when we did MP1, well, how can I launch more work from a given thread? Like different threads generate different amounts of new work. Well, the answer is not so much that you want to spawn off work, but you want to basically designate regions, again, determined by each thread, where you want to do something on them. And then you want to, and again, then you indicate, so each thread outputs, okay, here's a region, and then writes out the flags. And then you can use segmented scan to basically operate on each of those, regions, and then you can come back and continue working on them when you're done with whatever segmented scan, you apply it with segmented scan. So quicksort, if you're familiar with that algorithm, is kind of the most obvious kind of candidate. If you haven't heard of quicksort, it's basically a sorting algorithm where you say, for each element, am I larger or smaller than some value, which you have picked out of the array? And if I am smaller than, I'm going to move myself off to the left. And if I'm larger, I'm going to move off to the right, so that after the operation, you have the contiguous, everybody who's smaller is to the left, and everybody who's larger than that value is to the right. And then you kind of, for each of those two domains, you again subdivide them by picking values out of those two subdomains, and you continue to sort values, and that's actually a very fast sort. And so when you're doing a serial program, you will actually basically just say, okay, I've sorted everybody into left and right, and I'm going to now call myself recursively on the left half, and then on the right half, and then combine them again. If you want to work on parallel, what you want to do is, again, this pattern of determine if I'm lesser or greater than the particular value, then do a very simple sort, basically just move myself off left or right. Actually, in this case, you can do it with a scan or two, and then operate again on the regions. But because those regions, you go from one region to 2 to 4 and so on, you want to operate on each of those regions independently without having to think about how big is that particular region and how many are there. And again, segment scan is the perfect pattern for this. So there's many algorithms which have this general characteristic. And so if you're working on something which kind of does this divide and conquer step often and recalls itself recursively in a serial implementation, then, and you want to really port that, then think about how you could use segment scan in this kind of pattern I described to you, because it's often very useful. So the next thing I want to talk about is sort. So sorting elements or key value pairs is probably the most common operation which computers do. I mean, I've heard my professor back in grad school say that basically 30 to 40% of all computer cycles in the world were consumed by sorting algorithms of various kind. I have no clue where he got that number from, if I was making it up, but sorting is probably the most common thing, and it's also very, very useful. So again, if you remember back to MP2, where you had to bin particles and then operate on those particles, some of you said, well, I'm just going to compute my bin, just leave everything in place, and then I'm going to go off and compute, if you remember part 3, the nearest neighbors just as is. And then you were kind of surprised that things weren't very fast. And we kind of pointed out to you that you want to operate that so that your inputs are somewhat coherent. That is, you want to operate in a fashion where the particles which are in a given bin are usually also, neighboring threads in a thread block. And the notion here is, which we mentioned to you kind of in the performance tips, you want to have execution be coherent, so that if you have branches, the threads, the neighboring threads will probably execute the same control flow path. And so if your threads are of the same region, and you're doing the same thing per region, or very similar things, you have a much greater chance that you will be going down the same control flow path as if they're just random from some region, and some of them might be on the border of your domain, and some of them might be in the middle, and who knows what. The same is true, actually, even more so for memory accesses. If you remember, if threads in a warp, that is the 32 threads which make up a warp, if you remember, all go off and access random portions of memory, that's going to be much, much less efficient as if they go off and access a one chunk of memory. Somewhere between 16 and 32 times more efficient. So if you can figure out the memory access pattern of your threads based on some region, some ID that you can come up with, and you can sort on that ID, you can get tremendous efficiencies in terms of how the hardware can actually execute your program. So sorting for more coherency, both control flow, how your program is executing, and the data access pattern is often a very good idea. It obviously depends on how much work you want to do per step, but usually you're doing enough work that, thinking about determining what region or what part of your domain you're in and sorting on that is a very good idea. And I mentioned already previously that this common pattern is you operate in one kind of domain, one kind of coordinate system, you could say. You figure out, oh, I need to process this subset of threads, the data of this subset of threads in a different way, and this other subset in yet a different way. And if, kind of as you saw in MP3, those are sparsely interleaved, that basically all the threads, all the warps have to do both, or all the different domains that you have, you're going to be less efficient as if you just sort first so that each of them just goes down one path or doesn't have to do anything, as example in MP3, and then if you just have them operate and do everything. So binning, which we did in MP2, has some of the same effects as sorting, right? If you said, well, we binned, and then if you operated on those bins, again, you got back your control flow coherence and your kind of data access coherence. Now, binning is weaker than sorting, right? Sorting gives you a global kind of fine-grained order. Binning just means that, yes, I am in the right kind of bin, that can be very coarse or very fine-grained. So the question is, which one should you use? Because you couldn't make binning, if it's specialized, faster than a generalized sort. But the good thing about sort is that there are standard implementations available for CUDA, and actually they're very much optimized. So it's a question of, do you know exactly how many bins you're going to use and how to write an optimized binning kernel, and is it worth your time? And if it's not, because you're going to have a lot of these steps, you can think of, well, instead of binning based on my whatever the key is, your bin ID is, I'm just going to output my bin ID and I'm just going to call sort based on that. And so it's a question of A, how much effort, calling a standard sort is very little effort, and B, of how many bins do you have. If the number of bins is very comparable to the number of elements, you're basically doing a sort anyway, so do call a sort. If you have very coarse bins, like you have 4 or 8 or 16 bins and you only have a couple of million elements, well then binning might make more sense if you know how to implement an optimized binner, which hopefully now you do. And so if you know anything about sort, then you know that there's kind of this dichotomy between saying, I want to sort on arbitrary keys, aka my key, the values I'm sorting on can be strings of arbitrary lengths, they can be trees, whatever, or I'm just going to sort on a value which fits inside of a 32-bit or 64-bit integer. If you can do the latter, then you can call radix sort, which sorts on keys of a fixed length, which is not that long. And radix sort is usually much faster than comparison-based sorts. It's certainly algorithmically more efficient. It's O(n) as opposed to O(n log n). But so if you know the number of domains or keys or bins or what have you that you need, and there's a simple mapping, and there are 2 integers, and the number of these is not larger than, let's say, 4 billion, which is an unsigned 32-bit int, which probably is, then radix sort is the way to go, because again, we have a fully implemented version, and that is very, very fast. Okay, so I've talked enough about segment scan, enough about sort, so now I'm going to talk about pattern, which basically is a combination of the two. So you might have heard of MapReduce. MapReduce is actually an old concept from functional programming, for those of you who have heard of that. More recently, it was kind of popularized by Google. Some folks from Google wrote a paper, which I think was published in 2004, on basically how they applied this pattern for a large distributed system, aka their Google cluster, to do very large batch processes. And the idea here is basically you are given a function which takes a single input, and outputs a key value pair. The value can be anything, right, from a single number to an arbitrary kind of data structure. Your key can usually also be anything, but you can think of it as just a single value. And then you basically apply the function to a domain. Very similar to CUDA, where you call a kernel on a grid. MapReduce is basically calling a function on a domain. And actually, we'll see next week with Thrust that you can apply similar ideas to CUDA and to GPUs. So this kind of illustration, which I've kind of stolen from the original presentation of that paper, and it shows this. So you have some input, again, very similar to CUDA. You apply the map function, which basically actually, so it takes your user-supplied function, and each instance of that map function with the user-supplied function outputs a key and a value, or sometimes multiple, but always these pairs. And then there's a step called group by key, which is completely inside of MapReduce. And group by key is just sorting based on the keys, right? And so then what you get out is, for each key, I have all these different values which have the same key. And for the key 2, I have some number of values, and so on and so forth. And then there's a second task, which is called the reduce task, which then generates the final output for each key. So if you think about it in a parallel implementation, what is the first step? This is basically very, very similar, or almost exactly the same, as it's what you guys did in MP1, right? For each element in a domain, in an array, apply some function and give me one output. No communication between the different instances of map, no looking at all the other data, just give me one input, I'm going to give you a certain number of outputs. And then there's a sort, which I just talked to you about, and then there's this reduce step. And as you'll note here, this is not kind of the reduce, the one global reduce that Jared talked about when he was talking about scan. Here you're basically reducing each of these domains. What this really is, this is a segmented reduce, right? So the same way as reduce is the first half of scan, you can do a segmented reduce, which is the first half of segmented scan. And this is exactly what MapReduce does here. And so this applies very nicely to the kind of distributed huge cluster systems that Google has, but it also applies very nicely, to any program that you write in CUDA. So this overall pattern is basically, if you don't know, the exact communication pattern, or if you just want to have one generic implementation to which you can pass simple functions which do reduce and do some input on one element, then MapReduce might be kind of the way where you start off just to see if it works. And then you can think about more about the communication patterns and so on. And so, as I mentioned, so you have in here basically the most trivial kind of applying a function to a domain, which you saw kind of hopefully in your first week, what we taught you. Since you can output a variable number of key value pairs, you can think about that's a scan, right? You have to figure out how many outputs do I have overall. So that's a scan here. And there's a sort, which we just talked about. And then there's a segmented reduce, which is the first half of the segmented scan. So overall, this is just a combination of all the steps that we talked to you about over the last 2 lectures. And I want to point out again so that, in MapReduce, there's always this talk of, oh, you just need to output a key value pair, right? The value, again, it doesn't have to be, you don't have to kind of limit yourself to thinking about this is just one number, right? So kind of the most kind of common example people bring up for MapReduce, kind of certainly in the Google context, is, okay, I'm going to give each web page in the whole web to one particular map task. And so it's going to go through the text of that web page, and for each word, it's basically going to output a key value pair where the key is the word and the value is 1. Right? So you're going to take one input and you're going to get somewhere between 1,000 and 1,000,000 outputs for each map task. Then you're going to sort based on all the keys, which is basically all the words that you found on the whole web. And then you're going to reduce. So basically that's going to be a sum. And what you get out is a histogram of the frequency of words on the web. That's kind of again, the most common example for MapReduce in the context of Google. So if you think back, that's basically very similar to the histogram you guys did in MP2. Right? But instead of colors or simple values here, it was just an unknown number of keys and an unknown number of bins in your histograms, and again, just simple increment, increment, increment for the actual frequency. And So you can do the same thing again with CUDA if you want to, but you can obviously do much more kind of sophisticated stuff. Like, let's say you want to operate on a graph, and you want to say, I'm going to give each node in the graph to a particular task, look at its neighborhood, try to construct some, different subgraph based on that, and then you can give it, each value would be a subgraph which you're combining in certain ways. Lots of graph algorithms work in that way. And you can come up with everything else. So kind of this combination of segment scan, output a variable number, doesn't matter how many, sort, and then reduce based on those keys, again, is a very generic pattern. It's a nice combination of scan, sort, and segmented scan. And can often be kind of a good starting point for tasks which you don't really know, kind of think about a good structure just to get going. And then once you have that, then you see where the bottlenecks are, and you think, well, how can I simplify that? And the sort phase, again, is kind of reliant on, well, two things. Since you have no control usually over the sort phase, right, you have to output it in a way which is a standard kind of key format so that the library can sort on that. And so usually that's just a 32-bit integer or a 64-bit integer. And that basically relies on, again, what I mentioned previously, that there are standard and optimized implementations of sort, especially radix sort. And so you don't pay for something where you probably don't really need a full sort. But you don't, you're still going to pay some overhead, but it's not going to be as bad just because you're dealing with an optimized version. And the reduce phase, right? So I said the common examples are, I just want to sum over a region, or I want to do the max or the min, and that's, that's the most common cases. But again, don't limit yourself just to that if you're thinking of pursuing this pattern. So finally, I'm going to kind of change tracks and talk about kernel fusion. So kernel fusion is the idea that, okay, you're doing something in kernel A, and you're doing something in kernel B, and if the way the data from kernel A is passed on to kernel B is very straightforward, like all the inputs at index I from kernel A get passed to, the same index to kernel B, and that outputs one value again, why don't you just combine A and B into a single kernel? And what this gives you, especially in the context of executing a GPU, is you don't have to you don't have to allocate an array for intermediate values, so that can be a big savings. But B, you don't have to write out that intermediate value to memory and then read it back in just to do another step. And for those of you who have started on MP3, and hopefully that's all of you, this should look familiar, hopefully, right? You have a kernel which says, well, I'm going to take my output and I'm just going to determine, is it, even or not? And then based on that, I'm going to do something with scan. Yes, hopefully. So what if just you think about fusing those two kernels, combining those two kernels. So instead of outputting the value of even in a separate array, you just calculate it right before you start your scan, and then you pass the value of flag straight into your scan. So again, the benefit here is if you're doing it this way, right? If you write in flag equals to blah, 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 that's going to be stored in a register. And then it's going to be passed straight in a register to the next part of your code, which does a scan, and then go into shared memory. So especially if you're not doing that much work, like in this case of is even, you're doing very little work, you can get a nice speed up because you have much less memory bandwidth than you have, execution bandwidth. So if you're doing just adds, you can do a lot more of those, or multiplies, than you can store and load from global memory. So generally, as I said, you want to have something where the way you get your data is very straightforward, right? The most straightforward way is you're accessing the data in exactly the same way for kernel F as for kernel G. And then it's very straightforward to say, okay, I don't even need the intermediate thing. I can go straight from the intermediate result from F into G and move on. But you can also think that's also possible if the pattern is, a simple permutation of indices, then you can still do it, right? If you're taking an input which is at index I plus n for the first kernel, and then outputting it at I plus n, and the second kernel takes it at input from I plus n and outputs it at I, just a straight offset, no. You can still combine the kernels. Or if you have some other kind of weird sorting behavior, but which you have analytic insight into, that is all possible to kind of combine kernels and have the same result. The other thing you can do is, or the other pattern, which is kind of often is, if you are basically reducing multiple values into one and then passing it on. So the first kernel could be doing some partial sum or min-max over a region, and then you're doing something to each element, right? Think of segment scan. Then you can think of, okay, when I have the output of that region, and so the output overall, the domain overall of the second function is smaller, kind of by definition, because you've reduced multiple values into one per, in the first one. You can just pass those values straight into your second kernel, and you can have a benefit there in terms of the hardware, how it executes. So the other kind of common thing is you have one data access pattern. So here are kind of a generic optimized stencil. So stencil codes are kind of usually those where you have your index is I, and you're going to look at values at I minus 1, I, and I plus 1, right? Lots and lots of blur, image averaging, convolutions, min, max, lots of image, video, kind of regular grid codes in scientific computing. They all have this pattern. So they're all called kind of stencil patterns. So let's say you have this pattern, but you actually use it multiple times for different things. Again, very common in kind of regular grid codes and certain image processing codes. So let's say you've optimized one of them, and it's now really optimized. You're using as little memory as possible, memory bandwidth as possible, and so on. But you have 20 more, right? So do you want to, each time you find an optimization for one, you need to copy that to all the other ones? So one way of kind of using kernel fusion is to basically say, no, I'm going to have a generic optimized stencil kernel, and I'm going to pass in a functor. So functor is just a function which operates on data which you give it in a particular manner. So what can a functor be? Here, right? You say, let's say I want to do a box filter, FIR or whatever. Then you can say, I'm going to pass this in to my generic optimized stencil kernel, and hopefully have nice performance. And I don't have to rewrite the same optimized code and again. And that's, especially once you start, iterating on your code, you will always have something, oh, I forgot to propagate this one optimization from, the place where I did it to everybody else, and I introduce subtle bugs. So in terms of software engineering, this can also be a good thing, especially if you have lots of kernels which are very similar, but not, totally identical. So, you can pass in a box filter. You can just say, oh, I just want to do the max, whatever. So this idea of passing in functions to a kernel, which is generic and has certain access patterns, you'll have a lot more about that next week when you have a lecture on thrust. But I just wanted to point this out as kind of this very common pattern for stencil codes. And if you want to, focus your effort again, not duplicate effort in terms of copy-pasting all the code and potentially introducing bugs, this is also kind of where you need to think about, or can think about, kernel fusion. So overall, actually I didn't have a wrap-up slide, so let me go back to the beginning. So overall, again, I talked about segmented scan, which is this kind of more fancier scan built on top of scan, which lets you operate on lots of regions of variable size all at the same time. And this is very useful in lots of different ways, which I hopefully have convinced you of. I talked about sort, which is probably even more useful in almost everything you do, especially apart from all the algorithmic things where it just makes your life easier and just isn't just necessary. It's also very useful for resorting elements so that you have some coherence in terms of data access pattern and control flow. That just that fact often gives you a nice big boost in performance. I talked about this generic kernel pattern of MapReduce, which is this combination of just applying a function to a domain, scan, sorting, and then segmented reduce or segmented scan. And it's kind of often a nice generic starting point for problems where you don't really know which pattern, which structure you should apply. And I talked about kernel fusion, which is can be nice both in terms of optimizing for the hardware, that is saving memory bandwidth, and also can be useful in terms of software engineering if you write a generic optimized kernel to which you pass different functions in. So with that, that's basically all I had. So that's the rest of that whole the talks for today. Any questions? Question?
For more, please visit us at stanford.edu.